Hello, everyone.
Hi.
Hi. That was awesome. Okay. Yeah, we're gonna talk about Malloc internals. Yeah. So, quick refresher on what Malloc is for those of you who haven't used it in a bit or just don't know. Um, Hopefully, this looks familiar now. So, Malloc and free, right? So that's um, like the function definition for Malloc there. You see, it just takes the size for how much memory to allocate onto the heap. That's what Malloc does. It allocates memory on the heap, and then it will return a pointer to the beginning of that newly allocated memory. So if you want to have something that lasts longer than just the scope of whatever function you're in, or for whatever other reason you need to put something on the heap, you use Malloc. Wonderful. And when you want to unallocate that memory and free it up, they're going to be used later by other things. Then you use the free method to free up the memory. What? Louder? Okay. You want me to repeat everything I just said, or? Please? Dude, it's Malloc, bro. Sorry, okay. Do we have a mic, Will?
No.
There's no mic?
It's just how it is.
Man.
You just gotta yell at me.
Okay. Alright, I'll wait. I'll shout out. Okay, chunks and allocation. So, got a nice little animation. There we go. So Malloc will allocate memory in what it calls chunks. That's actually the official word they use for it too. It's a gross word, but whatever. So you have chunks, and the minimum chunk size is aux20 bytes. That's 32 bytes. And the size is increment for these chunks by 16 bytes, right? So this picture here, you kind of see what a chunk looks like when it's first allocated. So it really starts at where it says size. That size and the AMP, those two things are usually referred to as that section is usually referred to as the chunk header. But really it's kind of part of the same 8-byte structure, right? And I'll get into what AMPs, what all those little flags are for later. But the size field pretty much is for metadata, and it just tells you how large the allocated chunk is. And then everything after that is the user data. In this picture, they refer to it as the payload. It's just the whatever you want to allocate onto the heap, whatever data you're allocating onto the heap, that's where it is. Okay? Cool. So, so when you actually call a malloc, the pointer that, the address that it's going to return to you, that pointer is going to be the start of the payload or the user data. And Malloc internally will use a different address, which is the where it says Malloc chunk pointer. It's actually 8 bytes before the chunk header. And that's how Malloc kind of deals with it internally. But when you run Malloc, you're going to get the user data returned to you, or the address for the user data returned to you. Okay, so about the chunk size field. So the size field is 8 bytes. And like I said earlier, it's kind of also referred to as the chunk header field when combined with the flags. And the possible sizes are aux20, aux30. It just goes up by increments of 16 bytes, right? All the way up until I think aux8 or something like that. I don't know. Yeah, and then you also have these different flags. So the last 3 bits of the chunk header they're reserved for these flags. And yeah, 3 of them. A is for non-main arena, which tells you that this chunk is not allocated in the main arena, and I'll get to it on what an arena is later. Nmap tells you whether or not it was allocated with Nmap versus Malloc. And then pre in use tells you whether or not the previous chunk is in use, or if it's whether or not it's free or if it's allocated, right? And that one's probably the most relevant one to the rest of the specifications. So yeah. Okay. And you also have this concept of the top chunk. So this is an unallocated chunk that takes up the rest of the heap. So if you look at this picture, we have 2 chunks, right? You have one here, one there. That's kind of laggy, but whatever. And then the rest of the heap is taken up by this top chunk. And it's got its own chunk header with its size and everything. And then the rest of that is just the chunk itself. It takes up the rest of the heap, right? So when you're allocating data with Malloc onto the heap, you're pretty much allocating it from this top chunk, and you can think of it as like you're pushing the top chunk down, right? Because you're just, you know, creating chunks on top of it. And yeah, okay. Now for our first demo. Hopefully this works. Okay, is that big enough? Maybe it's a little bigger. Okay. So, I'm going to run this Malloc 2. This was compiled with libc 2.23, and the reason why that's relevant is, well, I'll get to it, but yeah, just have that in mind. And I'll open it with GDB. Well, actually, let's first look at the code for this. Really simple. So all we're doing here is we're allocating some chunks with Malloc. We're creating a string just to show that we can, and then we're going to free those chunks, and we're going to see what that looks like. But first, I'm just going to show you what it looks like when we actually allocate them. Okay. Creating a breakpoint at main. Okay. So if we try to look at the heap now, right? This heap chunks, we're not going to see anything because, oh wait, hold on. I gotta do this real fast. Okay. Wait, there we go. So if we look at the heap, I'm not entirely sure why it does this, but at the start of the program, it allocates a bunch of chunks, and it looks like it's like the arguments to the terminal for some reason. It's allocating those. It doesn't do this in every version of libc, but this version of libc does this. So it's got a whole ton of like random stuff on it right now that the program didn't necessarily allocate, or like what I wrote in the C didn't necessarily allocate, right? So if you look, we're still right here. We didn't run this yet, but we're going to run this now. So I'm going to go ahead and say next. And now if you look at the heap, this chunk down here is the one that we just allocated, right? I don't know if you can see that. It's kind of like all the way at the bottom, but yeah. So this here, where I'm highlighting, this is the size field of the chunk, so the chunk header. And you can see that the size is set to aux20. So the one there is there because it's the flag for previous in use. But so ignore the one. The size is going to be aux20, so 32 bytes. And we can see 8, 16, 24, 32, right? It's this kind of highlighted purple thing. That's the entire chunk. And Malloc, so like when you run Malloc, the pointer that you're going to get to that variable, it's going to be this address here, the start of the actual user data, right? Whereas Malloc internally is going to be looking at this address, which is before it. So we'll just keep kind of running these and seeing how these chunks get. Oh, another thing to note. So I specified like the size. I said allocate only one, right? But we saw that there were like, it was a size aux20, even though I only said one. It's because the minimal chunk size is aux20. So even if you say like 1 or 5 or whatever, you're going to get a chunk of size 32 bytes. Yeah. And so this next one I'm going to run is, I said 33. So we're actually going to get like a chunk of size 48 bytes, right? aux30. So if we look at that, we can see that over here with this new chunk with size aux30. Cool. Let me see where we are right now. Just create another one. Getting string. We're gonna okay. All right. So yeah, that's pretty much what the chunks look like on the heap. Back to the presentation. So yeah, there is a vulnerability with this, right? Well, there was. So there used to be this vulnerability called House of Force. It was this attack. It was like published in like some fact paper. And the idea of this attack was if you get like a buffer overflow or something and you're able to overwrite what the top chunk size header field is, you can overwrite it to just like a really big number, which will cause an integer overflow, which is going to like pretty much say that the entire heap is now the top chunk. And with the entire heap being the top chunk, what you could do is you could then use Malloc again to allocate anywhere within the heap and do any kind of arbitrary write. And it's a pretty cool attack. But this was patched at that date, so it no longer works. And the reason why, what they did in the patch is they just created a way to verify the top chunk size headers to make sure that like, not something insanely large or getting messed with. Okay, so now the concept of arenas that I kind of like touched on earlier, I mentioned it. So an arena exists. The reason why we have arenas is to like, so you can have kind of multiple threads, right? It allows more than one region of memory to be active at a time. And every single arena has its own heap that it uses, all right? And the point, like what the arena does is it keeps track of all of the unallocated chunks. So whenever you free a chunk, it's going to get thrown into a bin, and there's like multiple bins, and we're going to talk about these bins too. But yeah, multiple of these bins, and they're all kind of kept in this arena. And yeah, and arenas are kind of created as needed. So when you run out of top chunk space, what happens is the kernel is going to try to like extend the top chunk space with like this SERK system call. And if you can't do that, then it's going to use mmap to actually allocate a new arena and just create a new heap, right? But yeah, so they're created as needed. Yeah, so free and fast bins. So one of those bins that the arena keeps track of is fast bins, and it's like a collection of linked lists, pretty much, and they're organized by chunk size. So for chunks of size aux20, it's going to have a fast bin. For chunks of size aux30, it's going to have its own fast bin. And whenever you free a chunk of one of those sizes, it gets kind of put into the associated fast bin, right? Up into a certain size. Fast bins are not used for like very large Malloc allocations. And we'll get to how those get handled later. But for smaller ones, it's fast bins, right? Yeah, so when you free two chunks, right, they kind of link to each other. Like I said, they're linked lists. There's like the user data part of the chunk will get repurposed to a forward pointer to point to the next chunk. It's just a way of pretty much so the arena knows where all the different chunks are. And yeah, so once it's in the fast bin, so once you like want to allocate a new chunk with Malloc, it's going to go through those fast bins and allocate from the top of that fast bin. So it's like a stack pretty much. Cool. So going back to here. We're now going to free that first chunk that we allocated. And if we look at bins, we can see that the fast bins, something was placed into it, which is great. That's what we wanted to happen, right? So if we look at fast bins, we can see that in the fast bin for size aux20, we have this address, which is the address of the chunk. So if we go to viz now, and we look at this address, 880, that's this chunk that we previously allocated. of size 20. And you can see that, like I said earlier, the Malloc is going to use the address of like 8 bytes prior to the actual chunk heading, right? So if we free another chunk now, and we look at fast bins, we can see that we now have A0, and it's linked to the one that we had earlier, right? So we look at viz now and fast bins. We go to A0, which is this chunk here. That's the next chunk. As we look here, that address is the forward pointer to the previous chunk, right? So this one up here. And yeah, so that's how it knows. That's how the arena knows how to how everything is in the fast bin. It's because they're all kind of linked to each other. Cool. So I'm just going to keep freeing these. And now if we look at fast bins, we have 2 fast bins now because those other 2 variables, C and D, they were of larger size, right? They were of aux30. Now we have a fast bin for aux30. You see that that is getting populated. So if we run viz now, that was these 2 chunks, right? And if we look at fast bins, we can see that the top of it, top of the fast bin for aux30 is this address here, which is the same as to this address, so this chunk. And the forward pointer for this chunk points back to this one over here, just like you would expect, right? How it's getting populated. So that's kind of how free works with fast bins, okay? Cool. And what's after that? Okay, so now when we allocate data again from that, it's going to allocate from those fast bins now. So let's look at fast bins again. You can see that we have 2 in the first, 3 in the latter. And then when we run next, look at fast bins. You see that now we only have 1 from the first one because it took that address that was there and it repurposed that chunk for allocation. So now it's allocated, right? And the same thing is going to happen for the rest of them, right? So I'm going to run, this command up here is going to run, and it's going to get rid of this next fast bin chunk in the aux21. And then when I run, when I'm allocating 33 bytes, it's going to allocate from the aux30 fast bin. So yeah, you can see that there's only like 2 things in the fast bin now, when there were 3 previously, and there's nothing left in the aux20 fast bin. Cool. Okay. So this is like the general structure of what these chunks look like, right? So when the chunk is in use, it's just that image that we saw before. You have its chunk header and its payload, and that's all, right? When the chunk is free, the payload gets repurposed to now it has a forward pointer and in some cases a back pointer. In fact, when it gets allocated to fast bins, or when it gets put into fast bins, it doesn't have this back pointer, it only has a forward one. But the other bins do use the rest of those things. And we're going to take a look at them now. So these are all the different bins. There's the T-cache, which didn't exist in the libc version that I compiled that previous example in. And T-caches, I have a slide on it, we'll talk about it, but it's like for smaller things. It's a lot like fast bins, but it's local to only the thread that it's in. Fast bins, which I demoed, which we saw. Then you have small bins, which smaller bins, but like larger than fast bins. And yeah, I'll get to all of these, but pretty much this is the order that, like, when you free a chunk, this is the order that Malloc kind of looks at it and says, okay, where are we gonna put this chunk? It's first gonna see if we can fit it into T-cache, and then fast bins, and then small bins, and then sorted bins, and then so on, right? So that's kind of how that looks like. Oh, and the reason why So like these small bins, unsorted bins, and large bins, they're actually all part of like the same array. They're just like used differently, but they're all actually in the same array in the arena. It's like the same structure thing. So that's why that's there, the bin thing. Okay. So how do bins actually like recycle and repurpose these chunks, right? So imagine you have 3 chunks, right? A, B, and C, and they're allocated onto the heap in that order. And then you want to free the B chunk, okay? So if A is free, so the chunk before it, then when you free B, it's going to merge backwards with A to create that larger chunk, all right? And it's going to do the same thing for C if C is also free. And it's going to merge forward to C to create like this big mega chunk, all right? And if that big mega chunk is then adjacent to the top chunk, then it just gets absorbed into the top chunk. Else, then it gets like put into the appropriate bin, right? So if all those get combined to be large, then it'll be put into a large bin, a small bin, or whatever. It's based off the size of the chunk, right? So now let's talk about these different things. So TCAS was introduced in GlibC 2.26. It was an optimization thing, right? And you can think of it as like kind of a private arena. So arenas are like shared between threads. Tcache is not. Tcache is local only to that thread. And it's pretty much, it works very similarly to how fast things work. It's singularly linked lists. And yeah, the only difference really is, well, the big difference is that it has less security checks. There are like a ton of vulnerabilities associated with Tcache that I haven't looked into yet, but they exist. Yeah. Then you have small bins. There are 62 of these, and they're all a fixed size. And they can only hold 1 chunk each. But this is pretty much like, look at this diagram. You have your small bins 1 through 62. My name's kind of cutting it off there. But you can see that they have the header, right? And then they each have a forward pointer and a back pointer to point to the next chunk and also the previous chunk, so that it knows if it needs to coalesce or merge with the other chunks, right? Yeah. And then the unsorted bin is kind of like a miscellaneous thing. It's another optimization strategy that was implemented, kind of like TCAS. It's like usually a lot of times when you're writing a C program, you're going to be freeing and allocating multiple chunks at once. And this is kind of exists in the realization of that. So if it notices like a ton of stuff was getting allocated recently and freed recently, then it's just going to merge all of those chunks into 1 chunk and then throw it into this like unsorted bin that is not organized by chunk size or whatever. You can have like small things or big things in there. And yeah, it's pretty much just a single linked list, kind of like fast bins is. Yeah, if you look at this diagram here, you can see that the sizes range from like 88 to 1008 to whatever, right? So large bins, these pretty much act exactly, it's a blurry photo, but like these pretty much act exactly like small bins, but instead of there being like 1 per size, they kind of cover a range of sizes so that you don't have like a million of them. And yeah, it's pretty much the same thing. They have the forward pointer and a back pointer, so they can coalesce if they need to, and so on. So from here, it's pretty much presentation. The next step is to like take this research further if you're interested in this stuff. So to look into Tcache attacks, unsorted bin attacks, because those things I know they exist. Finding ways to like force the usage of a certain bin would probably help create more interesting demos. And the other house of attacks, there's like a whole series of them. And it'd be also cool to look into hooking Malloc and free and seeing if you can do anything with that kind of stuff. Yeah. How was that, Will? Is that long enough? Okay, should I? Okay. Cool. Yeah, any questions? Yeah, what's up? You go first. Dude, I don't know. Whenever I find a cool picture, I just save it, and then like, I use it later in presentations and all. Yeah. Yeah, what's up?
Can you go back to the small bin slide real quick?
Yeah, sure. Yep.
So is that, it's like small bin 1, 2, and then goes up to small bin 62?
Yes.
So each of them hold 1 chunk each, right?
Yeah.
I'm a little confused how they're pointing to how it's like pointing to another chunk under the same small bin for each one. So like small bin one has like this one chunk that's pointing to another chunk.
Right.
How is it still only one each if it's pointing to another one still within small bin one?
That's a really good point.
It's not one, Daniel.
Yeah.
It's not one chunk each. It's ahead of a linked list for that. Yeah. So yeah, so that's
Yeah, it's like one chunk size.
one chunk size.
Yeah, so it's one chunk size. It's not one chunk. So like, for chunk size 16, there's one small thing. For chunks of size 24, there's.
Oh, okay. So it only has chunks of both sides.
Yeah. So that's how it works.
All right. I get it.
Yeah.
Perfect. Thank you.